All right, guys. So in this chapter, we will be learning about alternating current circuits or AC circuits. So we already learned a lot of different configuration for circuits where we learned about resistors, capacitors, inductors, and how we can have a circuit with just a resistor, just a capacitor, just an inductor, or any type of combination. We looked at the RC circuits, LC circuits, RL circuits, RLC circuits, and we could see, like, let's say, advantage or disadvantage, or type of application we can go get from different type of combination. But all of those circuits that we've studied up to this point used what we call direct current or DC, DC, let's say, circuits. They were DC circuits, meaning that they were connected to a battery, and those batteries provide constant voltage, constant current, and the current is always in the same direction when you connect your circuit elements to these batteries. In this chapter, we're going to be learning about alternating current circuits, because every time in your house you are trying to connect your phone to a charger or your computer, or basically using your power outlet in your house, you're actually using alternating current circuits, because your household outputs are, you know, connected as alternating current circuits. So we're going to learn here what is the difference um, between DC circuits and AC circuits, and what is the eventually the advantage of using alternating current circuits in the households. All right, so let's look at first in terms of understanding how voltage and current in your AC circuits, right, different from the DC circuits. One thing I already mentioned here is if you have a DC, let's say, think like this. So here's a battery with some kind of resistor connected to it. Let's say this is EMF source and this is your resistance. Well, this circuit provides you with a current that goes um, around from the positive terminal to the negative terminal. And then you can look at in terms of this EMF. Let's say if you look at the current, right? So this is EMF over the resistance. And because it's a battery, the EMF itself is always a constant, right? So let's say if this is 1.5 volts, then, well, it's a 1.5 volt EMF. Resistance is just, always a constant quantity. Then, for example, let's say it's 10 ohms. So then what you get here is 1.5 volts divided by 10 ohms. We get basically 0.15 amps or 150 milliamps. That means the current is going to be 150 milliamps or 0.15 amps, basically the entire time you're operating the circuit. So if you're plotting the voltage as a function of time, it's 1.5 the entire time. If you're plotting the current as a function of time, then let's say it's going to be 0.15 amps the entire time. So it's going to be a constant current, constant voltage. If we are using then the AC circuits, the battery here is no longer a battery, or like let's say the source is no longer a battery, but it's going to be what we call a generator. So generally, represented like this. So it's a power generator, and it's different from the battery in a way that the voltage, as you can see in this diagram over here, is time dependent, and the shape of that is basically sinusoidal. That means the voltage changes with time. So let's say 0, then it increases until it reaches some kind of maximum value, and then goes to 0 again, then goes to the negative V, then goes to 0, and back and forth. And you can see, right, it's alternating. So it's what you end up getting here is an alternating voltage. So it always goes back and forth between its maximum value and minimum value, so which is positive and negative. And when you take the measurements and put it on a graph, you will see that basically it's sinusoidal. Okay, so that means the voltage is time varying, and you can see, right, you can look at it as a period. How long does it take for it to go and get to its maximum value again. That means you can look at it in terms of frequency, in terms of, let's say, the period, and represent it as a sinusoidal graph. So in terms of the biggest difference, obviously, you get from that. That means the voltage. So this is lowercase v, and we usually use lowercase v if you remember when something is time varying. So then lowercase v delta v is equals to delta v max. That's basically the maximum current, sometimes known as a peak current, peak voltage, times sine of omega t. Remember, this omega t is the angular frequency, and we're gonna see that angular frequency can be represented a couple of different ways. But a lot of times, what we have here is this delta V, either known as a peak voltage or a voltage amplitude. Generally, that's the maximum output voltage of the source, either when it's positive or negative. So let's say in terms of generally here we can say maximum minimum, because one thing you should remember, right? So voltage is a scalar quantity. So when it's negative, so it's actually smaller value. So negative 10 is actually smaller than positive 10. So that's why we can say that, here you get maximum, here you get the minimum, right? So negative 10. That means what we get here is by just changing the type of power source we have, going from the battery into, let's say, for example, some kind of new AC source, could be generators, oscillators, or electrical outlets. Then right away we get oscillating voltage. Now this angular frequency is basically given in terms of radians per second. Okay, so this angular frequency can be also related to the linear frequency with the conversion factor of 2 pi. So omega equals 2 pi over f. But then if you remember that f, which is the frequency, is equals to 1 over the period. So we replace that, then omega is equals to then 2 pi over the period. That means that the equation for the voltage can be written in terms of frequency or in terms of the period. So delta V is equals to delta V max times then sine of, you can say 2 pi f times t, or equivalently you can replace frequency with the period and just write it 2 pi over the period times t. That means they all basically exactly, will give you exactly the same quantity. Okay. Now, frequency, you remember, it has a unit of 1 per second, but we define that to be hertz, and the period always in seconds. That means you need to always make sure to convert things into seconds. If the frequency of the period given in minutes or hours or days, right? Then you must convert it into seconds in order to plug in this calculation. All right, so you can see that, for example, the source determines the frequency of current in any circuit connected to it. And one of the things we have here is the electric power plant in US use a frequency of 60 hertz. So that generally, the 60 hertz is kind of like the standard in US. And this corresponds to angular frequency of 377 radians per second. That means if you do 2 times pi times 60 hertz, then you will get 277 radians per second. All right. So again, summarize this. Your voltage changes with time. So you can plot it, changing voltage as a function of time. And then what you get here is you get the amplitude. So this is the positive amplitude, and this is the negative amplitude. And in a way, you can think of, like, let's say, this function generators, right? This power outlets that provide you with the AC circuit, right? They basically vary, your voltage. That means your circuit depends on the voltage, and we're going to see its current. Also, since delta V depends on the angular frequency, that means you can change things with just the frequency as well, right? Because you can see delta V is equals to delta V max, then sine of omega t. That means just by dialing down or increasing your angular frequency, you can also change your voltage. All right, so one thing I showed you in terms of that the current in a DC circuit was equals to EMF over the resistance if it's a just a circuit with a resistor alone. Because the EMF was constant, the current was constant. But now you can think of, like, let's say if we have then the current in a AC circuit, then this current is no longer constant because, we can just represent it with a lowercase, right? So what you have here is it's proportional to the EMF, or the, proportional to the, voltage of the source that we're using. But this source is varying with time, right? So this source itself is varying with time. So then we can just say that this is delta V. So in a way we can say that current is equals to delta V, then sine of omega t, and this is, let's say, divided by the resistance. So let me rewrite this. So it's delta V with a lowercase divided by the resistance, but delta V lowercase is then delta V max times sine of omega t divided by the resistance. And in a way, delta V max divided by the resistance, this will always then give you the maximum current. So then you can rewrite it as maximum current times sine of, because those two together gives you maximum current, then sine of omega t. And that's pretty much what we're going to be able to see. All right, so but here what we can write down is the Kirchhoff's loop rule for this circuit, which is just two devices in your circuit, the battery and, well, the power source and the resistor. So then you have changing potential for the power source plus changing potential across resistor. Add them together, you get zero. That's a Kirchhoff's loop rule, where the sum of the alter potential difference is equal to zero. All right, so one of the things we have here is you can see that because everything changes with time, so a lot of times we can look at sort of like at the instant of time. So that instant current clockwise around the circuit, because one of the things we're going to see is that every time voltage changes, remember, so the graph, so see from here to there, voltage is positive. From here to there, voltage is negative, which means that polarity changes of the power source, which means then the current changes direction. And that's the main, the difference between current in an AC and the current in a DC. Current goes back and forth. So whenever the voltage is positive, current, let's say, goes clockwise. Whenever voltage is negative, then the current goes counterclockwise. That means it constantly changes. Clockwise, then counterclockwise. Clockwise, then counterclockwise. So back and forth. All right, so you can use a sign convention in the right figure. One of the things we're going to see, let's kind of clear this up. What we'll see here is if we kind of like using this for the loop, our potential difference across resistor is going to be negative. It's going to be a drop of potential, right? So that's probably I should have started with this in terms of then using this. We can say that IR times the resistance is equals to then delta V, and then basically plug in or whatever in terms of this is divided by R, then give you the current through the resistor, where then delta V was then the time varying the voltage, and then we plug in everything. Then what we will get here is this, right? So this basically ends up giving you the maximum current, where the maximum current is the ratio of the maximum voltage over the resistance. Then sine of omega t is carried from the time varying voltage equation. Then you get time varying current equation. So time varying current equation basically tells you that if you plot the current as a function of time across resistor, then you should be getting exactly the same thing, right? So you should be pretty much getting, try to make sure that my amplitudes are matched. So something like this. Okay. That means what we get here is we get, again, time varying current, because current is equals to I max times sine of omega t, where this will be then your I max. Okay. So here you can see that, again, always representing maximum current as delta V max over the resistance. And from here we get the value. That means Ohm's law, where V was equals to I times R, now can be modified this was for the DC circuit, where now it can be modified into I max times R times sine of omega t. Okay, because what we have here, we have an amp. This is basically for the AC source. And here's in terms of the diagram that we have, where you can see that the current going from A to B, basically, if you use the Kirchhoff's rule and go in that direction, let's say if you have, let's say, your loop like this, so if you go in that direction, then delta V is equals to negative IR. And if your loop then from A to B, but the current goes from B to A, then potential difference is plus IR. And then the same thing with the, delta V, right, equals plus EMF, or delta V equals negative EMF, depending if you're going from negative terminal to positive terminal or from positive terminal to negative terminal. That means, let's assume for this entire time our loop goes from A to B, then the change in potential will depend if you're going from in the direction of the current or the opposite direction of the current for the resistors, or from negative terminal to positive terminal, or from positive terminal to negative terminal of the power source. All right, so again, kind of like summarize everything. The current and the voltage, as you can see, right, you're given this diagram. Basically, both of them are sinusoidal because they increase, then reach maximum, then decrease to zero, and then you repeat the same thing basically in a negative direction. And you can see here is, for example, when you go to point A is pretty much gives you both maximum current and maximum voltage. That means you have the current reaches maximum, voltage reaches maximum, and obviously that happens at some time and certain very specific time and frequency. Okay, and then what we have here then between points A and B, the current and the voltage, right? Remember, in a way, the current follows what you do or what happens to the voltage, right? Because in any case, that it doesn't matter if it's AC circuit or DC circuit, the current is proportional to the voltage. That means if voltage is positive increasing, the current is positive increasing. If voltage is negative decreasing, the current is negative decreasing. So they're always going to pretty much more or less follow each other, in this circuit with a resistor connected to the power source. All right, so then between points A and B, so basically for this segment, you can see the current decreasing in magnitude and the voltage decreasing in magnitude, but both are still positive because, this is, remember, this is kind of positive domain and this is a negative domain. So as long as, it's above the T line, right, the T axis, everything is positive, even though it's kind of like decreases. Obviously, at point A basically represents voltage and current to be zero. And that's again following this. That means if the voltage is zero, the current has to be zero. And obviously, it's not something that just stays constant. It's just very specific instant of time. So let's say at this T, some let's call it some TB over here, right? That the current and voltage are for that instant basically zero. But obviously, the TA is the time when both of them are reaching their maximum value. Then you go from C, let's say B to C. What you get here for this region, now they're basically increasing, but in a negative direction. Okay, so they reach that negative V max or negative I max. So they start increasing, as a graph, right? But toward the negative direction until they reach the maximum value in the negative direction. So that, let's say, some TC, right? At that time they reach the maximum negative direction. That means that for time A, the current you basically get V max and I max. At TB, V is equals to 0, I is equals to 0. Again, so I'm using lowercase because, or you can, maybe you can say that V is, V max and I is I max. And then here both of them are 0. Then at times TC, then what you get here is V is equals to negative V max and I is equals to negative I max. Okay. Then starts increasing, And so basically going from, C to some point here, let's call this D, right? Then let's call this TD here is then TD is going to be then the P equals to the period, because that's going to be then completing one cycle. So here then again, V is equals to 0, and I's will be equals to 0. That means in a way, so this is, let's say, some time that we started with, right? So that, let's say that was the starting, time, and then we go and come back, and that will be completing one cycle. So that's kind of what we have. And both of them, you can see that give you a sinusoidal, right? That means it's not like one is sine, the other one cosine. So one of the things we're going to see that specifically for the resistor, current and voltage are what we can say is, are in sync. That means they are in phase. That means their crests are always, reach at exactly same time. That means TA here is when you have both for the, this, right? So that means you have Vmax and Imax. Exactly at the same time, they both reach the maximum. And exactly at the same time, they reach 0. Exactly at the same time, they have, maximum negative direction. And exactly the same time, they complete one cycle and things like that. That means resistors, right? In a way, very, at least there's some similarity between resistors in, connected to the DC circuit, the AC circuit, is that what you have here is what we're going to see a little bit later on. There is no frequency dependence. That means the current and voltage, across resistor, they don't change. That means, the resistor is a frequency independent device, because in a way what we have here is that resistance itself, right, is not a frequency dependent, let's say, circuit element, which will be different for the capacitors and inductors. We will see that capacitors and inductors can actually change, or basically, their value, right, of what we call reactance change if we change the frequency. But let's say if I have 200 ohm resistance connected to this function generator, well, this value will never change. Okay, this value will never change in terms of resistance in the circuit provided by this, by this resistor, doesn't change at all if you, let's say, change the frequency. And the reason here is because both of those current and the voltage are in phase. So if I change frequency of one, well, I'm, same way changing the frequency of the other one, and basically you get exactly the same thing. For example, this R here is V over I, right? And this is basically, let me kind of, give myself a little more room. So let's say R here is V over I, which is delta V max sine of omega t over I max, sine of omega t. In a way, you can see, right, this sine of omega t, and for the voltage, and sine of omega t for the current, well, we can, we can cancel them because they're the same. And that means, it just depends on V max over I max. That means, for example, in a way, what you're saying is that sine of omega t for the voltage and current will always be exactly the same, because if I increase the frequency here, I'm increasing frequency over there. And sign of argument for both of those will be always the same. So we can just cancel it out and then have the voltage is equals to then just V max over I max. Sorry, the resistance equals to that. And it will never change. Okay. So that's kind of what we have for the resistor. Okay. Another thing we can, sort of like, let's say, a tool that we can use to help us understand this AC circuit a little better is known as a phase diagram, or Phasor diagram. So the Phasor diagram is sort of like, it's a vector. Okay, remember, so we're dealing with potential and current, and those quantities are scalars. So, but we have this, a phasor, which is a vector whose length is proportional to the maximum value of variable it represents. And the phasors represent basically voltage and current. Okay, so you have, then you can write delta V max for voltage and Imax for current. That means we have two phasors, two vectors. One is a voltage, another one is a current. Okay. So then the phasor is put in a Cartesian coordinates, and then we can say that as values of those change, remember, so technically, they cycle like this, right? Which can be, represented as a, one full cycle, basically in a positive, then in a negative, which can be analogous to the positive and then negative, right? So basically a cycle like this. So we can put them together in terms of you can say, right, this represents the Imax for the current. That means that represents the current phasor. And what we have here is the current phasor, basically in phase, right, with the voltage phasor here. So then the blue here is the voltage. Okay, so the blue here is voltage. And what we have here is both of them, as I mentioned, right, because both of them are in phase, both of them exactly, according to this, have the same time zero, same time maximum, same time zero, and so on and so forth. So we put them together like that. And we can say that they change as, omega t, right? That means, remember, omega t is what? Omega t is just the angular displacement, right? Omega t is the angular displacement because it's angular frequency in weight times time. It pretty much gives you the angular displacement. And in this case, they both, in phase. You can say, right, the current and voltage phasor are in the same direction because the current is in phase with the voltage. Okay. So then what we can do here, we can then kind of like take a projection, right, of those. So you can say that phasor rotates counterclockwise at the angular speed, which is equals to the angular frequency associated with the variable. And then the projection of the phasors into the vertical axis, or let's say in this case, let's take the vertical axis. So these give you then the instantaneous values. Okay, so this will be your value of the IR. This will be your value of delta VR. That means instantaneous voltage and instantaneous current. All right, so again, so this phasor diagrams, right, are just basically a tool, allows you to, sometimes easily calculate some of the unknown values, because again, this is sort of like a geometric approach to this, and sometimes it's just easy to do some kind of like vector calculation, which you will see, especially for the inductor, capacitor, or combination, let's say, circuits. So you have a inductor and a resistor, or a capacitor, a resistor, and an inductor, right? All of those together. In that case, then you might have a little more complicated, let's say, configuration, and phasor diagrams can help you. Okay. So projection of phasor arrows into the vertical axis determined by sine function of an angle of phasor with respect to the horizontal axis. Right. That means you can look at it in terms of projection on the y-axis, which gives you the instantaneous value. Then projection of the into the, let's say, into the vertical axis determined by the sine function of angle of phasor with respect to the horizontal axis. Okay. So then the horizontal axis, then this can be basically in a way represented with the theta, even though you can say change in theta, right? But that's basically taking that theta initial here equals to 0. So you can look at that as the angle in radians, right? How it changes with respect to that horizontal axis. All right. Here's then in terms of why I mentioned, right, there's an advantage to this approach. So the phase relationship among current and voltage, so can be represented as vector addition of phasors. Okay. So for a single loop resistive circuit, like we have over here, you have a current and a voltage phasors, same direction in phasor diagram. Again, because the current and the voltage are basically, they're in phase. So if they're in phase, they're both of them in the same direction. But this is, again, I mentioned specifically for the resistor, just a single resistor in the circuit. When you have other configurations, you're going to see that this actually no longer true. The current and the voltage no longer in phase for capacitors, and they're no longer in phase for the inductors. So we have to then, let's say, be able to use this phasor diagrams to do some type of calculation, and sometimes make the calculation a little bit simpler because the geometrical approach to those is sometimes simpler than analytical. All right, so let's see what we have. So the average value of current over one cycle equals 0, because you go like this and you come back. So 0, 0, right? So you can think like this. So current maintained in the positive direction for the same amount of time. That means this is the current in a positive direction. And then you have the same amount of time, the current in a negative direction. So if you add them together, basically you get 0. Okay. That means in a way, it doesn't matter if you start like that, or technically you would have started like this. So if you go like this or like that, doesn't matter, because you're going to get still, average current for one cycle to be 0. Okay. All right. So because again, the voltage changes with time, and frequency, and same with the resistor, and they are in phase in this particular instant. One thing we can do here is we can calculate the rate at which the energy is dissipated in the resistor, or the energy that energy delivered to the resistor. Remember that equation was pi at the P equals I squared times the resistance. That means power equals the current square times the resistance. Technically, we can represent that several different ways, right? It could be like, let's say, V squared divided by resistance, or IV, right? Current times voltage. But in this case, I here is the instantaneous current in a resistor. That means in order for us to do the plot, we need to look at, instantaneous current through the resistor for some kind of, I don't know, 5 minutes, 10 minutes, and then take those measurements and plot it in a diagram. One thing we can see is that for the current graph, if you do the current versus time, well, you get both positive and negative. But when you're doing the power, over time, that means, what is the rate at which energy delivered to the resistor? Well, what you get here is you get power equals to, so basically I max, so it's I square, right? So then I max sine of omega t squared, then times resistance. Okay, which means that what you get here, you get I max squared, then times sine of square omega t, then times the resistance. Okay, that means when you're doing this power graph, okay, so what you get here is you can see, right, you're always going to be positive, because this portion of the current that is negative, right, when you're doing current versus time, well, you're squaring it, so that means the graph, your graph will always be a positive for the power that you get, right? And one of the things we have here is that the average, the current square is equals to 1/2 of the maximum value. That means whatever we have for the I max, see, the average is right here, where average here was 0, because you have both positive and negative. So positive and negative together combined gives you the average current of 0. Here, average of current here is 1/2 of the maximum, which is that line over there, which you can see, right, goes through exactly the half of the, basically this segment over here. Okay. Again, because the rate is proportional to the square of the current, no difference whether the current is direct or alternating, which means that whether, let's say, you're always going to get a positive voltage, right? So if you're looking at the instantaneous, let's say power using instantaneous current, in a way, you're always going to get the same value, right? So in terms of positive value. All right, so whether it's sign associated with the current positive or negative, again, doesn't really matter, because we are squaring, the current in this particular, calculation for the power. All right, so average value, is something of importance for the AC circuits, and that's because look at the measurement of, or the possible measurements of the current as a function of time. Can you make a some kind of measurements of the current that is not instantaneous? For example, something that can you represent it as some for the entire period, of the oscillation or something like that. Well, most likely not, right? Because current is constantly changes. So when it constantly changes, then you can't really, say anything about the current, unless you specifically talking about the current, so like instantaneous current. Yes, you can give me current at this time, or current at that time, or current at this time. But that's about it, right? So you can tell me, okay, here's the current at that instant, here's the current at that instant, here's the current at that instant, but you can't really generalize that. But one thing we can do here is when we talk about then the average value, it is easy to get the average value by using what we call root mean square or RMS values. Okay, that means instead of talking about instantaneous current, because basically with instantaneous current we need to know which time are we talking about specifically. But then this RMS current or this RMS quantity, right, allows us to then have one value that is true for the entire, let's say experiment. Okay. Again, the square root mean or the average value of the square of current. That means basically you can write the root of the mean square. That means you have the here. So root means this is known as a RMS value. So RMS value for in this case, right, which is the current RMS, so equals to the square of the root or average of the current square. Now the same thing then we can have for the rearranging where we as I said, right, so then average current, if you look at in terms of current average, this is equals to 1/2 of your the maximum value. So if it's equal to the 1/2 of the maximum value, so if you take that and plug it into inside the root, right, inside the square root, then what you end up with is basically this equation, right? So you end up with 1/2 I max. Sorry, I forgot to square that one over there. So that means if you plug in over here, so it's going to be, I max square over 2. Since I max is squared, it can come out of this, and then but 1 over square of 2, right, doesn't, so it becomes square root of 2. That means this is basically IRMS equals maximum current divided by the square root of 2, which then will be 0.707 I max. That means it's roughly about 71% of the maximum value. That's what this RMS value represents. But one thing we have about this RMS value, which you can see, right, it's always constant. It never changes. That means we can then just use this RMS value to represent the current in the circuit. And every time we need to let's say anything else, let's say instantaneous or something like that, then if I know the RMS value, then I can use that to calculate the maximum current, right? Because if I have this, then divided by 0.707, that gives me I max. If I have I max, then I can use that then, let's say, to get the instantaneous current or average current or something like that, and do some calculation. Now, what do we have in terms of RMS value? Why do we want to do that RMS value? Well, we're going to see that because we can measure those, right? We can actually measure those using the voltmeter or ammeters and things like that. All right, so same way I can then, when I'm considering RMS value, then the power, which was I square times R, then can be changed into the average power, which is then can be given in terms of RMS value. So current RMS current square times resistance. Okay, that means I can then say that same thing can also be true for the voltage. So because then delta V, right, changes with time, and I can just basically say that delta V square R average is, and then from here just basically rearrange and calculate then the RMS voltage value. which is again 0.707 times delta V max. Again, that means if I have a graph of the voltage as a function of time, so then this will be my graph. Then I can say some kind of, RMS value for the voltage. Just like here, I can have some kind of RMS value for the current. Okay. Again, the advantage of using RMS value is because, for example, 120 volt alternating voltage from electric outlets that you have is actually a RMS value. So when you look at 120 volt, it's the RMS value, and that means the maximum value actually is 170 volts. So, and again, RMS values are useful because we can measure them. That means if you have a voltmeter or an ammeter, that means device that can measure voltage and current in your circuit, imagine if you connect it to your circuit to measure the voltage. Well, you can't, right, if it's AC circuit, because voltage constantly changes, goes to maximum, zero, negative, and so constantly changes. So your value is going to shift every second. Well, but we want to be able to do some kind of measurement, right, with AC circuits. Well, what we do here, we have then our multimeters, right, voltmeter or ammeter, set to measure the RMS values. That means our AC ammeters and voltmeters designed to read those RMS values. And with RMS values, then we can, once I have RMS value, well, times square root of 2, then I can get I max, right? If I have then VRMS value times square root of 2, then I can get, V max. Then I can solve for V, because now I have V max, then sine of, then if I have omega, and I can then measure as a function of time, then I can calculate, let's say, my V. Because a lot of times, let's say, how do I find that? Well, we can, use the RMS values. Then omega and time, those are sometimes, omega is something that can be fixed in your function generator, and the time is something that, you can measure, using a stopwatch. All right, so that's kind of, in terms of what we have for these values of current and voltage in a circuit with a resistor connected to some kind of function generator. Let's look at some examples here. You have a 100-watt light bulb is screwed into a standard 120 volt RMS socket. Find the RMS current, the peak current, and the peak power. Again, the peak power or peak current, those are the maximum values of those, right? All right, so in terms of then what we're given here, we're given here, let's say the power, right? But that's the maximum power, right? Sorry, the average power, 100 watt, the light bulb, and 120 volt. Those are RMS values, and let's say that's basically the average power. So I can say that this color here, I can say that P average numbers was equals to, then from the equation that we just learned, right? I can say that this is basically I square RMS times the resistance. But also remember, so the power can also be calculated from the voltage times current. So that means this will be the VRMS times IRMS. Okay. Or I can also calculate this as VRMS squared divided by the resistance. 3 different ways I can pretty much calculate the average power. Okay. Now then from here I can remember that average power is related to the voltage and current with this relationship. So I can say that P average, remember, so then technically P average is given us as 100 watts, and then VRMS is given as 120 volts. So P average is equals to IRMS times VRMS, and then from here I can solve for the IRMS, which is voltage or power over voltage. Average power divided by the RMS voltage. So 100 watts divided by 120 volts. So we get 0.833 amps. Okay, that means this is basically my RMS current. That's part A. Part B says then the peak current. Well, if I have this, remember, right? So then, IRMS is equals to maximum, which is the peak, right? Maximum current divided by square root of 2. That means my maximum current is equal to square root of 2 times IRMS. Means square root of 2 times 0.833 amps. So then we can calculate this to be 1.1785 amps. Okay. Then for part C, what is the peak power? Well, again, same way, right? What I have here is, so average is equals to basically, well, let me see, the peak power here, it will be in terms of the current. So let's see. So this will be then the average power divided by square root of 2. Actually, it was other way around. So this is average, this is peak, or the maximum. Sorry. So then just like all of them, right? So then I rearrange, then find the maximum power as square root of 2 times then the P average. Okay. So then right. So sorry, I made a mistake here. It's average is half of the maximum, then two times P average. So 2 times 100 watts then give you 200 watts. So that will be the maximum, the maximum power or peak power. Remember, from the graph, right? So the average is always, half of the maximum. All right. So let's look at then an inductor. That means our circuit, instead of a resistor, has an inductor connected to the function generator. Now, in this case, what we end up with is if you have an inductor, then again, you can look at it in terms of, doing like a Kirchhoff's loop rule. So if I do this, then delta VL, that means the voltage across inductor, remember, is equals to negative L DIL dt. This is from the last chapter. So then Kirchhoff's loop rule will tell us then having two devices, right, two circuit elements, a function generator or AC power source and an inductor, then we're going to have like delta V, which is the power source, plus delta V of the inductor equals 0. This is basically the Kirchhoff's loop rule around the circuit. But because we are going to be looking at the function generator going from positive to negative terminals, so this is going to be basically positive delta V. But for the inductor, then we're going to have a then potential drop, because if you going to add two things together and get a 0, one of them has to be negative. And in this case, because of the way we have our loop, this guy here is negative, which is then equal to L DIL dt. And subtract them to get 0. Okay, that means what we have here is then dV or delta V, that this is basically the time varying voltage, right? It's equals to L DIL dt, and I is the current through the inductor. Okay. Now, one thing we have here is the left side of the equation, delta V, is basically nothing but delta V max, then sine of omega t. Right? That means L times di dt is equal to delta V max sine of omega t. Then, for example, then if I divide both sides by L and cross multiply delta t, then what I will get here is this. DIL is equals to then delta V max. Remember, I divide both sides by, so dt and L is L dt. So DIL will be delta V max over L. Then sine of omega t dt. Okay. then obviously one thing we can see here is, remember, so our goal was to, see how we can derive the equation for the current. For the circuit, it was very simple, right? So basically, delta V equals, I times R, and I equals delta V, delta V max, sine omega t divided by the resistance. So, but in this case, you can see, right, this is a, basically going to be an integral form, right? So that means in order for us to get the current, we have to, integrate both sides. So the left side then is then IL, but then the right side, you have the integral of the whole thing. Well, obviously, delta V max, L, those are constant and can come out of the integral. Then in a way, what we're doing, we're integrating just sine of omega t dt. Okay. So, which is, relatively straightforward, integration, you know, in terms of the what we're going to get here is to substitution, so for example, we take x equals omega t, then dx is equal to then omega dt, so then dt is equals to 1 over omega dx. So then make a substitution, so we can say then IL is equals to delta V max over L, then integral of sine of x, then 1 over omega goes here, so then dx. And just basically integrate this. So then this is going to give us integral of sine of x is just negative cosine x. So then it'll be negative delta V max over omega L, and then cosine, and then plug back the omega t instead of x. So cosine omega t. That means what we end up here is this is basically the equation for the for the current. Okay. Now we can already see there is a little bit of difference in terms of delta V and the delta I, or the current. Okay. So we can see that in terms of delta V for us was delta V max, then sine of omega t. And now what we have here for the current, right, delta I technically, or in a way I can just write V like that. So not necessarily delta V, just V, same thing. So the same thing here, I can just write I. So there's IL, right, I across the inductor, is then negative delta V over omega L, sorry, delta V max over omega L, then cosine omega t, which means we can see that in a way, if I'm looking at and comparing, so I have a sine omega t in one case, then cosine omega t in another case, but I can write this one as IL as negative delta V max over omega L. So then using where then cosine omega t, sorry, cosine omega t equals negative sine of omega t minus pi over 2. That means, I can, kind of incorporate the negative and cosine omega t into that, and just rewrite this as delta V max over omega L, then sine of omega t minus pi over 2. Okay, that means current and voltage are out of phase by exactly pi over 2, or 90 degrees. So that's, in this case, you can see, right? So that's basically already a difference compared to the resistor where they were in phase, but here they are, out of phase. That means, again, so V is equals to delta V max, then sine of omega t, and then the current here is equals to delta V max over omega L, then sine of omega t minus pi over 2. Okay, that means here what we can see is that those two are out of phase, right? Out of phase by exactly, pi over 2 or 90 degrees. One thing to remember is that whenever we're using these calculations, we need to keep our calculator in radian mode so that, you know, those arguments over there, right, they must be in radians when we're doing those type of calculations. Right, so the last thing, hopefully you guys can notice that this is coefficient in front of sine, omega t minus pi over 2, which then technically represents maximum current. That means our Imax is equals to delta V max, then omega L. So we'll come back to that. But let's look at what happens with the current and the voltage being out of phase, let's say across the inductor. If we put both of them together in one graph, you can see that the graph on the right side gives you that exactly, you know, pi over 2 difference, right? So that if you plot, so then this the blue graph basically gives you the voltage, where you can see, right, this point A is no longer, you know, which is the, you know, the maximum for the voltage, no longer is in phase with the maximum of the current, which is basically somewhere over there. Okay, and the same thing when this is 0, it's this 0 at point, you know, point F, and when you have then the negative current, so that means everything is basically shifted by pi over 2. That means the current in the inductor equals 0 at point D, you know, where then that point basically coincides with the maximum voltage. All right, so then what we can say here is, because of that, we can say that the current in the inductor always lags behind the voltage by 90 degrees. Okay, that means it lags behind the voltage by 90 degrees of pi over 2, which is a 1/4 of a cycle in time. Okay, that means what we have is that voltage, which is maximum value, 1/4 of a period before the current, which is the maximum value. That means, you know, this is the time difference between them, right? And that's basically represents how long it takes for the current to reach the maximum, and that's exactly a 1/4 of a cycle after, you know, basically, you know, in terms of after that the voltage already reached the maximum value. So that's why we say it lags behind, because it always reaches the maximum after the voltage already reached the maximum. It always reaches 0 here, right? Let's say after the voltage already reached the 0 over there, and so on and so forth. And we can also present, you know, the phase diagram for this, where now the voltage is exactly the same, let's say, as we had for the resistor, but the current now is basically, you know, 90 degree, can you see, right, pi over 2, or 90 degree lagging from the voltage. Okay, that means they are out of phase by 90 degrees, and always, you know, because for this particular case, inductor, you know, for the inductor, the current lags behind. So then we basically make sure that, you know, remember, so our positive direction is counterclockwise. So we have the voltage first, and then the inductor 90 degree from that. Okay. So one thing we have here is, so when we go back to that, you know, equation for the current, which is equals to negative delta V over L, omega L, then cosine omega T. So for this basically the original one, and then we can kind of shift it to the, you know, to sine omega T minus pi over 2. We can see here that it reaches maximum value when cosine omega T equals plus minus, you know, plus minus 1. That means, remember, so this is the maximum value, right? This is the maximum value. And this is basically when this guy here is equals to 1, then the current here is its maximum value. Okay. That means one thing we can say here is IL equals then I max, and this is equals to then delta V max divided by, assuming that cosine omega T is equals to plus minus 1, and delta V max over omega L. Okay, so then this is basically the instant of time, right, when the current would reach the maximum value. Okay. So from here we can note that maximum has units of amperes, delta V max has units of volts. That means, in a way, what I have is this, right? So this is volts, at the top, and I have to divide by something in order for us to get amps, because on the left side I have current, which is in amps. On the right side I have voltage divided by omega L. Well, omega L together then have to give me a unit of ohms, right? Because amps is only voltage over the, ohms, right? In terms of resistance. So then what we have here is this. That means omega L technically has units of resistance, okay? That means this omega times L, this quantity here, represents a resistance in the AC circuit when you have an inductor in the circuit, okay? That means, in a way, this inductor in the AC circuit acts like a resistor. It acts like it would be as if it was a resistor. That means the combined unit is ohms. Okay. And in a way, then what we can do here is we can assume that, this quantity omega L. Remember, one thing we have about omega L is that L is the inductance value of the inductor. It never changes. But omega is the frequency, of the circuit, and that's something that can technically easily be changed. That means every function generator has 3 dials: one for the voltage, one for the current, another for frequency. That means it depends on the frequency. And one thing I have here is that you can see, right, I, which is equals to IL, delta V max, which we can assume is a constant, but then divided by L, which is also a constant, but then I have omega. And then just because I have omega over there, makes then the current as, a frequency dependent in this case, right? So that means, the maximum, this is the maximum current. That means maximum current reached a different, you get different maximum current, different peak current, depending on what your angular frequency is, okay? For the resistor, that was not the case. It was just delta V divided by R. That's it. There was no angular frequency dependence. But here it is. That means inductor reacts differently in terms of offering opposition to the current differently. And you can see right here, I max proportional to 1 over omega, which means that this quantity, right, in terms of that it has as a resistance, it changes with frequency. That means, for example, how much it can resist. Remember, resistance in the circuit basically is to control the current. So in this case, inductor acts like a resistor, but it doesn't act like a resistor, actual resistor would, because actual resistor that we just looked at, a few minutes ago, that resistor is just basically, always the same and constant, regardless what frequency we have. This, let's say inductor, when it resists the current, basically gives you opposition to the current, it also depends on the frequency, okay? All right, so one thing we can see here is that this product of omega L, we're going to define to be inductive reactance, X sub L. And we're going to write that X sub L is equals to omega L. So technically, this is you can think like this. So this is the resistance that inductor provides, right? So resistance that inductor provides. And then we can write the maximum current as maximum voltage, then divided by the resistance in the circuit due to the inductor, X sub L. Okay, but one thing you need to understand that this, what we call technically inductive reactance, right, is frequency dependent. You can see, right, in a way, when I have here is, let's say X sub L as a function of frequency. Well, when frequency is 0, X sub L is 0. And when frequency increases, X sub L increases. That means how much it resists to the circuit, to the current, right? Well, omega or linear frequency doesn't really matter, right? They're basically the same for us, just a factor of 2 pi. So then omega basically increase gives you the XL increase. Omega decrease gives you XL decrease. That means the resistance is strongest at the lower frequency, at the higher frequencies, and the resistance is weakest at the lower frequencies. That means, if you want to decrease the resistance in the circuit and increase the current, you don't have to replace the inductor. All you have to do is just dial the frequency down, and then the opposition to the current in the inductor decreases, and that means you have more current in the circuit, which you can see, right? The smaller this number, the larger the maximum current. Okay, that means this is kind of like what we have about the maximum current in the inductor, because see, maximum current in the resistor was Vmax over resistance, where the resistance itself did not depend on the frequency. It was always the same. But here, then you get frequency dependent. They're already time dependent, but now also frequency dependent. Let's say values of the maximum current. Okay, so this is consistent with Faraday's law. Greater rate of change of current in inductor, so larger back EMF. So larger back EMF translates to increase in reactance and decrease in current. That means when you have an inductor here, right? So higher frequencies generally give you larger current, because current, we see that, right? So the current in the inductor is maximum current, then sine of omega t minus pi over 2, but still, greater the frequency, higher the current. But higher the current, then inductor try to resist more, right? It gives you a larger back EMF. Remember the Faraday's law, Lenz's law, right? There is a induced EMF, induced current, try to oppose the change in current, and which means that at the higher frequencies, it tries to oppose more, because when you start increasing the frequency, you increase in current, and there's a change in flux to the solenoid, right, to the inductor. So then you try to then resist by introducing stronger resistance to that by stronger back EMF. All right, so that's kind of like then what we have for the inductor. That means inductor acts like a resistor, but it's a resistor such that it's a frequency dependent. Okay, it increases with the frequency. Okay. And here we have the voltage value as well, right? So for the voltage, remember, so this was the voltage of the inductor, negative L di dt, where negative L di dt, then basically you take the derivative of the current. IL was negative Vmax over omega L, then times cosine omega t. Well, if you take that and take the derivative of that, then the derivative of the cosine is basically a sine. So we get then, well, that negative, sorry, I think the derivative of cosine is negative sine. So that negative and negative cancel out, but there was already negative in the equation. So that one basically stays. So then this L will cancel with that L. And also the derivative of that will give us omega. That omega then will cancel with this omega. Let me kind of show you here what I mean. So if we do dIL dt, so I have then negative Vmax over omega L. Then I have first take the derivative of the cosine, so it becomes negative sine omega t. So those negatives cancel out. And then we take the derivative of the argument, which give us basically omega. So those omega cancel out. So that means this derivative of dIL dt just equals to then Vmax over L, then sine of omega t. And then because there was already another L over there, that will cancel with this. Then we get basically the value of Vmax. Then going back, and from this equation, we can see that Vmax is just the product of Imax times the inductive reactance, right? Delta Vmax equals Imax times X of L. So then, this is basically what we have for the delta Vmax. It's the amplitude of the voltage. So Imax times XL, and then sine of omega t. Right. So that's basically the value for the time varying voltage in the inductor. Okay. Now let's look at the capacitor. So a capacitor behaves a similar way as inductor, we're going to see, because one thing we have here is when you have a capacitor, remember, so again, using the loop rule, we have delta V plus delta V of capacitor equals 0. Right, so remember, so the delta V of the capacitor is basically Q over C. So then delta V, we're going to then, using the loop like this, we will see that this is just basically minus Q over C, and this is equals to 0, which means then from here, where Q is, remember, the charge on the capacitor, and because we go from such that there's a potential drop, so then we basically end up with looking at the equation. If I rearrange, right, so then I have delta V is equals to Q over C, or Q is equals to delta V times C, right? But then delta V here is time varying, which makes the Q time varying, right? So it's equals to then, delta V is, this delta V, it becomes maximum V, then times sine omega t, that's what the delta V is, then times C. Okay, but remember, usually when we start with this, our goal is to derive, so we already know the equation for the voltage, that's basically given from the function generator. Now, what is the relationship of the current to that voltage? Well, we right now found the relationship of the charge to that voltage, but we know that well, current here is just dq dt, right? So dq dt, that means taking the root of that of q as a function of time. So we can see then this is delta v max times c, those are constants, and then we're just basically doing the dt of a sine of omega t. Okay, so then this will give us, let me just v max c, and then sine of omega t is just cosine omega t. And then we introduce another omega because of this argument of that cosine, so another omega. All right, so let me write here. Then the current for the capacitor is equals to V max, then times omega, times C, then times cosine omega t. All right. So now because there is no negative in this compared to when we had a negative when we derived the equation for the current through the inductor. So then here what we can say is that cosine omega t can be rewritten as this. So cosine omega t is then equals to then sine of omega t plus pi over 2. Okay, so plus pi over 2, that means kind of we want to do that to see that if we represent both of them in terms of sign, are they in phase or out of phase? That means if I replace, because they're equivalent, right? If I replace this, I'm going to have V max times omega times C, then times sine of omega t plus pi over 2, so that I can see that, again, those two are basically, out of phase, right? They're out of phase by exactly pi over 2 radians. So now, again, 90 degree or pi over 2 radians, out of phase for the voltage, and a current, that means voltage across capacitor is basically out of phase, from a current by exactly pi over 2. Okay, that means, just writing all those things, we can see that, yeah, they are indeed pi over 2. And the next step will be to look at the graphs, how they, current and voltage graphs now different for the capacitor in the circuit. And you can see that this time what we have here is the voltage is basically, the voltage is lagging by 90 degrees, or we can say the current is ahead by 90 degrees. Because, for example, the current reaches the zero or the maximum earlier than the current the voltage, and then the current reaches 0 earlier than the voltage reaches 0. Okay, that means what we can have here is, again, so going from looking at the graphs, we can see that here, earlier reaching current maximum compared to voltage maximum means that if I'm doing the phasor, the diagram, right, for the voltage phasor, which is let's say same as was before in terms of for the Vmax. Now the current here is ahead by 9 degrees or pi over 2. That means since it's ahead, so I have to make that in a second quadrant. So Imax is then positive, and it's basically ahead of the voltage by exactly 90 degrees. In terms of then this equation for the current through the capacitor, omega c delta V max cosine omega t. Again, we can see that when cosine omega t is plus minus 1, then the current is the maximum, and which means that this is basically is our maximum current. So that means I max is equals to omega c delta V max, okay, delta V max, which means that if if we're looking at sort of like, let's say how those things are related, then I can say that delta V max is equals to kind of rewriting the Ohm's law. So it's equals to then I max, then times the resistance in the circuit when there's now a capacitor. That means if I divide both sides by omega c, right over here, you can see that this what I end up with this omega times c. Then to complete sort of like, let's say Ohm's law, I can see that this 1 over omega c then plays a role of opposition to the current in this circuit with the capacitor connected to the function generator. And that's kind of what we have, right? So then what I can do here is I can say then this 1 over omega c is then represent this opposition to the current, and we're going to represent this x as a reactance again, sub c, which is x sub c is the capacitive reactance. So it's 1 over omega c. Then I can rewrite then the equation for the current as the voltage, which is a driving, let's say mechanism, and then the reactance is the opposition mechanism. That means the voltage divided by the resistance or reactance in the circuit. Okay. And again, one thing we can see here is this reactance is frequency dependence. So we can see that, for example, if I'm doing, x sub c as a function of omega. So let's say, what is omega? What is x sub c when omega is 0? When omega is 0, then you get 1 over 0, which is basically, infinitely high. And then that means, when omega is 0, your reactance is basically the largest. And then as you increasing omega, then capacitive reactance then starts decreasing. That means it's highest when basically the frequency is lowest, and it's lowest when frequency is highest, which is exactly the opposite of the inductive reactance. Inductive reactance was highest when frequency was highest, and lowest when frequency was lowest. Capacitive reactance is exactly the opposite. It's highest when the frequency is lowest, and lowest when frequency is highest. Okay, so that's kind of like the difference in a way that we can see, right? Again, capacitor in a way acts like a resistor, a device that gives you an opposition to the current. But in this case, again, it's a frequency dependent opposition, and the frequency can determine how much opposition it can give you to the current, right? By changing the frequency. That means even if you have the same voltage and same current, by just changing the frequency, you can change how much resistance it gives you. Then without changing voltage, you can change the current, right? So in this case, you can change the maximum current by just varying the frequency. Right. So let's look at RMS current. So this, again, RMS current you can calculate for all of those, for the voltage, for the resistor, for the inductor, for the capacitor. So this is in terms of, let's say, RMS value of the current in the capacitive reactance, right? It's just the RMS voltage divided by the capacitive reactance. And I mean, the reason we're using RMS, again, remember, we can measure RMS. That means you take a function generator, connect the capacitor across the function generator, use a voltmeter and ammeter to measure RMS values, and then you can calculate actually how much resistance the capacitor gives you. Because these values, right, RMS values, are easily measured by our multimeters. That means every value can be then represented in terms of this. So, for example, then the delta V for the potential difference across capacitor, then is delta V max sine omega t. But because delta V max, not from here, but delta V max is equals to current times x sub c. So current max times x sub c. I can then also replace the delta V max with that. Okay, which means as frequency of the voltage sources increases, capacitive reactance decreases. That means maximum current increases. Okay, which means that by increasing frequency, you are actually decreasing the reactance in this case, right? You're decreasing reactance and you are increasing the current. The maximum current increases. Okay. Where generally for the resistors alone, maximum current is just a constant value, never really changes. Okay. All right, so so that's kind of what we have for the reactance. So we have, that means you have circuit with just a resistor, you have a circuit with just the inductor, and you have circuit with just a capacitor. And each one in AC circuit, acts like a current opposing circuit element. That means your resistor gives you resistance to the current, inductor gives you resistance to the current, and capacitor gives you resistance to the current. That means they have different function, right? That means you can see it's not just a let's say energy storing device. It's actually also gives you opposition, and they also give you that a little bit in a let's say DC circuit case, right? You could remember the current doesn't just go into instantaneously the maximum value, right? It would just basically slowly go to the maximum value when you have a DC circuit with that. So, but here obviously you have something that is more complicated, more a little bit different, right? The inductor gives you, let's say, reactance that frequency dependent, same with the, let's say, the capacitor. All right, so let's look at some examples here. So an inductor has a reactance of 100 ohm at 80 hertz. What is its inductance and what is its reactance at 160 hertz? Okay, that means we start with basically getting the reactance. That means X sub L, because it's an inductor, is equals to 100 ohms. Okay, so, and what we can say is that frequency F is equals to 80 hertz. Remember, when it's given in terms of hertz, that's the linear frequency. Okay, but we know that this is just basically can be easily used to find omega, which is then 2 pi times F, right? So it's always like omega is equals to 2 pi times F. And what we have from here is that X sub L is equals to omega times L. That means we know that reactance equals to the angular frequency times the inductance. From here, then inductance, let's say this is part A, L is just basically X sub L divided by omega. So we have 100 ohms divided by 2 pi F, which is 80 hertz. Then we can calculate the inductance of being 0.20 Henry. All right. So part B says, what is the reactance at 160 hertz? Well, which isn't that, okay? So then now that we have inductance, it's not something that changes with frequency, right? So reactance changes with frequency, but not the inductance. So then X sub L is equals to omega L again. So then this is then 2 pi times 80 hertz. Then times not 80. Now we have 160 hertz, which is like double it, right? So 0.2 Henry. Then what we get 200, right? We get 200 ohm, which makes sense because we just doubling frequency gives you double the reactance. All right. Here's another example. A circuit consists of 2 ideal AC generators and a 25 ohm resistor, all connected in series. The potential difference across the terminals of one of the generators is given by V1 equals 5 volt cosine omega t minus alpha, and the potential difference across the terminals of the other generator is given by V2 equals 5 volts cosine omega t plus alpha, where alpha is equals to pi over 6. Use a Kirchhoff loop rule and trigonometric identity to find the peak current in the circuit. And for part B, use a phasor diagram to find the peak current in the circuit. So basically, we first use the mathematical approach to find the peak current, and then we use the graphical approach, right, using the phasor diagrams to find the peak current. All right, so now it talks about mathematical, the trigonometric identity. And one of those trigonometric identities is just basically because you have basically two sinusoidal, right? Let's say voltages. You can see, right? So here we're given V1 as 5 cosine omega t minus alpha, V2 as 5, again, 5 is just the maximum value, right? So 5 cosine omega t plus alpha, where again, alpha is equals to pi over 6. So the identity that we have here is this. So like a cosine theta plus cosine phi is equals to 2 cosine 1/2 theta plus phi, then times cosine of 1/2 theta minus phi. Okay. That means, basically we have this identity. Okay. If we do the diagram of this, the circuit diagram, it could be so two function generators connected like this to a load resistor. So generally, again, function generator kind of given as a circle with a sine function in it, like this, right? So we can say that this is, let's say, V1, this is V2, and this is R. Okay. Now, then what I have here is if I have then my loop like this, then that will give me equation of basically delta V1 plus delta V2 plus delta VR is equals to 0. Okay. But it basically ends up then being V1 plus V2 minus I times R equals 0. Okay. So yeah, if you want, you can just write like that, IR, the current of the resistor. So then from here, I can just then write the IR is equals to V1 plus V2 divided by the resistance. Okay. Now, in a way, this is the equation that we want. That's the equation for the current. At least not the peak current, but for the current. Remember, then we can then use to find the peak current from there. Peak current will be then the maximum value of this the current function that we will get. All right. So the idea here is that well, we have two V's, right? So because this is going to be equals to so V1 is 5 cosine omega t minus alpha, then plus 5 cosine omega t plus alpha, and then this is divided by basically the resistance, right? So let's say 25 ohms. That means one thing we do here is we then use this identity, right, for the voltage or voltage sum. Then from here I can rewrite this as I sub R, right, which is the current through the resistor, equals to then. So here I have so if I kind of combine, so I have then let's say 5. Okay, so that means, see, both of them have 5, so I can factor out 5 and then apply then the identity. So then the identity will be 2, then cosine of 1/2, then I have theta plus phi. Okay, theta plus phi means that it's omega t plus alpha, sorry, omega t minus alpha plus omega t plus alpha, which means that alphas cancel out, and then you have omega t plus omega t, so I get 2 omega t's, right, inside, technically. But we continue, then this basically, I wrote this first part. Then let's write the second part, which is then again cosine 1/2, then theta minus phi, which is omega t minus alpha, right? Then minus, then will be omega t plus alpha, so minus omega t minus alpha. Well, here then the omega t is going to cancel out, and I'm going to get negative 2 alpha, right? So then this is divided by 25. That means I sub r then equals to, I think I might have room on another page. Let's go to there. Right, so let me write this here. So I sub r is equals to, right, so then kind of combining those together. So I'm going to get 10 volts. Then cosine, once then I apply the pi's, pi over 6 for alpha and everything. So then I'm going to get then cosine of pi over 6, cosine of omega t. Okay. And then this is divided by 25 ohms. Okay. So then this can be simplified as 8.66 volts times cosine omega t. Then I divide this by 25 ohms. Then what I will get here is 0.346 amps, because it's volts over ohms, cosine omega t. That means this is basically going to be my equation for the current. Okay. Well, then from here I can see that this is then is my Imax, because Imax cosine omega t. Okay. That means my peak current Imax is equals to 0.35 amps. There you go. So that will be then my calculation for the peak current using the the loop rule, using the the voltage, time varying voltages, and the trig identity. Okay. So next, what we're going to do here is we're going to then use the phasor diagrams to do that. So for the phasor diagrams, then so this is part B. So remember, so what we have here, we basically using the voltage as a vector, right? And for the voltage as a vector, now we have 2 voltages, right? So we have V1 and V2. All right, so let's see. Here I have this equation for I, which is equals to the voltage as a vector divided by the resistance. So usually you can just use absolute value for that. And we know that there, pi over 6, right? There was like alpha, right? Pi over 6. So then I can represent this as, so like, let's say, and remember the vectors are completely, independent of the circuit diagram. So one thing I can say here is this. So for example, if I have coordinates, I can just put them anywhere I want. But let's say it's easy to see that, remember, one of them was theta minus, alpha, and alpha is pi over 6, which is, 30 degrees. So in a way, I can take in theta to be 0. For example, I can say that here's the first one, V1, because it's, minus pi over 6. The other one was theta plus pi over 6, which means I can write this, do the second one like this. So this is V1 and this is V2. This is basically plus pi over 6. Like that. And then you can see that if I basically as vector add them together, I can just use, let's say, the parallelogram method, and I can see that what I end up here is with a vector like this. Okay. So I end up with a vector like that. Okay. So using that vector, I can see that it's like having 2 vectors where their y components, basically, if I kind of like do this y component of this one, y component of the other one, and I can see that, they're going to cancel each other because everything about them is basically exactly the same except the direction. So which means that I'm only looking at the components along the x-axis for both of them, and both of them are the same. Both of them are 30 degrees from that. So then V, the net, right, can be calculated as the sum of the two of their x components, which is 2V cosine theta, or cosine alpha, right? So like, let's say cosine alpha in this case. And since V1 x is technically going to be V2x because of the quadrants, right? So I can just say 2V cosine alpha, doesn't really matter. And this is basically their, the peak ones, right? Which is, 5 volts for both of them. That means this becomes basically 2 times 5 volts, then times cosine of pi over 2, or, 30 degrees. So then the magnitude of this vector, right, resultant vector, basically this is how we do the magnitude for that, is just 8.66 volts. Okay. That means in a way what we're saying here is that we're just adding their x components, so we get 8.66. You can see, right, it's a very easy way of finding then the magnitude of that resultant vector, so right, the maximum value. So then the current will be then the magnitude of the resultant voltage, which is 8.66 volts, then divide by the resistance, 25 ohms, and that basically will give me 0.345 amps, which is exactly what we got over there. Okay, that means I can just round it to be 0.35 amps. That means I could do this calculation both using the equations of the voltage and current and Kirchhoff's loops and just add them all together, or we could just do that graphically and just get that. All right, here's one more example. An AC source with an output RMS voltage of 36 volts at the frequency of 50 hertz is connected across 12 microfarad capacitor. So we want to find the capacitive reactance, the RMS current, the maximum current in the circuit, and we want to see, does the capacitor have its maximum charge when the current has its maximum value. We'll try to explain, the reasoning behind that if, let's say, our answer is yes or no. All right, so let's write down what we're given. We're given that RMS voltage is 36 volts. All right, so then the RMS voltage is equal to 36 volts, frequency 60 hertz, and the capacitance 120 microfarad. So those are our initial given values. Then for part A, find the capacitive reactance. All right, so capacitive reactance, there are two ways you can find it, right? One is that X sub C is equals to then voltage, right? So divided by the current, either RMS or let's say maximum, doesn't matter. But here we don't have this equation. We don't have the current. So then what we do here, we use the second equation for the X sub C, which is in terms of 1 over omega C. So that means this is 1 over 2 pi F times C. So 1 over 2 pi times 60, then times 12 times 10 to the negative 6 farad. Then we can get the capacitive reactance to be 221 ohms. Okay. For part B, it says, what is the RMS current? Well, now that we have reactance, so I can go back to that equation to find RMS current, because RMS current is equals to VRMS divided by the capacitive reactance. So this will be 36 volts divided by 221 ohms, and that will give us 0.163 amps, 163 milliamps. Part C says, what is the maximum current in the circuit? Well, once you have RMS, then you can use that to find the maximum or the peak current, because peak current, IRMS, remember, is equals to I max over square root of 2, which means I max is equals to square root of 2 times IRMS, which is square root of 2 times 0.163 amps. So that will give us 0.230 amps. That's the maximum current. Now the last one says, does the capacitor have its maximum charge when the current has its maximum value? Okay. Well, remember what we have, right? So this is a capacitor, and for the capacitor, the voltage is out of phase with the current. That means it is a 90 degree. Remember the voltage is lagging 90 degree relative to the current. So the current reaches its maximum value sooner than the voltage, which is 1/4 of a cycle sooner than the voltage reaches its maximum value. From this definition of a capacitance, the capacitor reaches its maximum charge when the voltage across it also is maximum. Remember, so I gave you the equation, Q is equals to V max, right? Let me look at the equation. So it was V max times C then times sine of omega t. This was basically for the charge. But for the current, that was, let's say, I max, but then it was cosine omega t, right? Cosine omega t, which means that, those both also are of phase, which means the maximum charge and maximum current never happen exactly same time, okay? Because of the current is sine omega t, cosine, which is the derivative of the, Q, ends up being cosine omega t, and then being, out of phase by 90 degrees. All right, so here's one more example. A 200 millihenry inductor is connected to a North American electrical outlet where the RMS value is 120 volts and frequency is 60 hertz. Assuming the energy stored in the inductor is 0 at t equals 0, determine the energy stored at t equals 1/100th of a second. Okay. So now, this is something that I haven't, let's say, give you equation yet for the time varying energy. But one thing we know here is we already have looked at the equation for the, inductor. So that was the magnetic energy across the inductor was 1/2 L times I squared. But, the only difference here is that this is basically time varying, current, right? So this is I sub L squared. The idea is that we said the question is that assume the energy stored is 0 at t equals 0. But obviously, what we have here is that this IL is equals to I max then sine of omega t. Okay, so that's basically what I have, which means that this is basically 0 taken to be at t equals 0, for example. Now, in terms of then what we have is we're given RMS voltage. The RMS is equals to 120 volts. And frequency given as 60 hertz. Okay. So one thing we can do, we can then basically use this to calculate the RMS current, because in order to look at anything, I need to plug it into this equation where I need first to find what is my I max. Okay. So the RMS can be used to find RMS, current RMS, which is voltage RMS divided by the X sub L. And then X sub L, remember, is just omega times L. And we are given the L, right? The L is the 20 millihenry. The voltage, 120 volts, divided by 2 pi times 60 hertz, then times 20 times 10 to the negative 3 Henry. So that can give me then RMS current. Okay, so that will be 15.9 amps. So then RMS current then can be used to find the maximum, because then maximum current is equals to square root of 2 times IRMS. This will be square root of 2 times 15.9 amps then I will get 22.5 amps. That means that will be my maximum current. Then coming back to this equation for the current, time varying current, then I have then I max, then sine of omega t. All right, so then from here, I can then plug in the values because I have my maximum current, 22.5 amps, then sine of my angular frequency, so it's 2 pi times 60. Then the t here is, we're given as 1/180th of a second. So that means just basically 1/180th of a second. Okay. So then if we do this calculation, so then this will give us 19.5 amps. 19.5 amps. Which means that if I come back and look at the magnetic energy, so 1/2 times L squared. In this case, then I have 1/2 times 0.2, 20 times 10 to the -3, which is my Henry, right, which is inductance, then times 19.5 amps squared. Then I can calculate the amount of energy that I have now stored. That's 3.8 joules. So that will be then the energy stored.